Hey, I'm the Devil, and welcome to my MTH Cribs.
Hi, I'm your host, Catherine Wallace, and this is Drunk History. On today's episode, we have our special guest, Georg Cantor. Cheers! Okay, Georg, what do you got for us?
Okay, here. So there's this guy, Herman Henkel Engels. Not the ankle part, though. And he's like, there exists nowhere dense, there does not exist nowhere dense sets with positive outer contents. This is like 1870s.
Oh, okay.
Yeah, so they're long dead. So
Long
we can
gone.
offend them. Ankle, pinkle, whatever. And then there's this other white guy, and his name H.J.S. Smith. And he said, yes, there does, and I will show you. And so he's like, okay, say take the closed set 0 to 1 and divide it by m parts.
Okay.
And then you take m minus 1 parts, get rid of one of the parts.
Okay.
And you divide that by m parts.
Okay.
And then you take m minus 1 of those parts and divide that by m parts.
No.
And then you just keep going on and on and on.
Forever.
Forever. And this is a counterexample, because this is a nowhere dense set with positive outer contents. And so now, today, we would call that like a generalized version of the Cantor set. Very
Okay.
general. But no one fucking cared.
Okay.
At all.
Alright,
No
alright.
one-
I know I should have.
Well, yeah, you shouldn't. And then there's also this guy. I'm gonna take. Is it okay if I take my shoes
Please
off?
make yourself comfortable.
Okay, so there's also this guy named Carl Gustav Axel Harnack.
There's another guy.
Yes, they're
Oh my
all
God, it's all
white
men.
men. All the white men. And he was like, I'm gonna work on the fundamental theorem of calculus, specifically an extension.
Okay.
I don't know what it is. Don't ask me.
I don't know either.
We're gonna come back to this though.
Okay.
Just keep him in the back of your mind. And then I came on, Georg Cantor. That's
Finally!
me.
Okay.
I know, the best in the world. And I was working on this like everywhere dense set stuff. It was like the 70s, 80s, 1870s,
Okay.
19th century. That's how time works. If you're curious. And I was also working on fundamental theorem of calculus. And
Did you go into that further?
Ooh, yeah, well, it was like the discontinuous functions, and I was working on that kind of stuff.
Alright.
Is it okay if I lay down?
Please. Stay with us though.
Okay. We're almost done.
Okay.
Okay, so I wrote this paper, and it had the Cantor function in it.
Okay.
Right. And so I wrote this paper, and I was like, Harnack, you ignorant slut. You're wrong. You couldn't be closer to the truth. And I said, look at this function. I'm going to call it Cantor function.
Okay.
I'm
Oh
impressed.
yeah, we love a person who loves themselves.
And so I made this function. I didn't write how I found the function anywhere. So,
Well, why not?
Well, it's
Are
a
you just like a
mystery.
silly little goose?
Yeah, a
Or-
little silly little goose.
Okay.
Okay, and so I didn't want anyone to know. I just came to my head and I wrote it down in this paper.
Okay.
This letter to frickin' Harnack. I said, this is a counterexample.
Okay.
And therefore, thus, the Cantor function came to be. It was born, and ta-da, that's it.
Okay.
Any questions? No, you don't.
No.
That's
Okay.
what I thought.
Thank you.
Because I don't have the answers.
You can fall asleep now.
Mm-hmm.
Cantor dust. It's uncountable. Good morning, Trevor. I hope you have some good news for us today.
Well, Catherine, I definitely don't. But I will tell you what's happening in hell today. The devil got a new staircase installed.
Really?
No, not at all. But we do have breaking news from the university campus on Monmouth, Oregon. Students are learning about the Cantor set and Cantor function.
Oh, we've heard reports that the Cantor function uses the complement of the Cantor set.
Definitely, if we look at this image right here, it might make it a little more clear. If we let k naught equal 0 to 1, and then take the middle third of k naught, we can define k1 equal to 0 to 1/3, that closed interval, union with 2/3 to 1. And then taking the middle third of each of those intervals in k1, we can define k2 as 0 to 1/9, 2/9 to 1/3, 2/3 to 7/9, and then 8/9 to 1. And we can keep doing this forever, actually. Might make some of you nerds out there a little mad, but we can define the Cantor set as k sub infinity, so that the very last one, if it were to exist. But if it does please you, and if you are really upset, we can define it as the intersection of all the k sub n's.
That seems like quite the clunky definition, Trevor.
It definitely is, but there is a way to simplify it down, but it requires the use of a base 3 system. So first, note that 0.999 going on forever equals 1 in the base 10 system, and then 0.222 going on forever equals 1 in the base 3 system. And so, using this system, as we did with base 10, we can let k naught equal 0 to 1, k1 equals 0 to 0.1, and 0.2 to 1, and then k2 equal to 0 to 0.1, 0 to 0.01, 0.02 to 0.1, 0.2 to 0.21, and 0.22 to 1.
Of course. So you could say that the Cantor set just contains all points whose base 3 expansion contains no ones.
Precisely.
So how big is that set?
Well, that can get a bit tricky. As many of the current Math 312 students took 311 last term, they learned about countable and uncountable sets. This is something that they probably do not remember whatsoever, but it's something that they did learn, and they did learn about different sizes of infinity. The Cantor set is uncountable, but it does have a length of 0.
How does it have a length of 0?
Well, we'll head back to our base 10 system for this. So again, if we let k naught equal 0 to 1, that has a length of 1. And then k1 would have a length of 2/3, k2 would have a length of 4/9, and so on. And then so we would have k sub n having the length of 2/3 to the n. We know that the Cantor set is made after an infinite amount of iterations, so its length would be the limit as n approaches infinity of 2/3 to the n, which equals 0.
What about the actual Cantor function?
The Cantor function is built in a similar way as the set is, in stages. So our first stage, we would have y equals x on the interval 0 to 1. That would be stage 0, and then stage 1 would be having that same picture, just with 1/3 to 2/3 as a flat line at y equals 1/2, and then diagonal lines connecting it to 0, 0, and 1, 1 respectively. In stage 2, we add flat lines for 1/9 to 2/9 and 7/9 to 8/9 at y equals 1/4 and y equals 3/4 respectively. And again, we're adding diagonal lines connecting these flat lines. We keep doing this an infinite amount of times, and we get the Cantor function.
It's quite an interesting function, Trevor. So this function is monotone and increases on the interval 0, 1, but it's flat at all points not in the Cantor set.
Right.
Since the Cantor set has length 0, all points not in the Cantor set must have length 1. Therefore, at almost every point of this function, the slope is 0.
Exactly. Something else that was noted is that the function is continuous despite it closely resembling a step function.
So if the Cantor set has length 0, its complement has length 1, what is the length of the curve of the Cantor function?
Well, if you make a horizontal line from 0, 0 to 1, 0, and then a vertical line straight up from 1, 0 to 1, 1, that length is 2. And if you take the line y equals x on 0 to 1, the length is square root of 2. That's found using the Pythagorean theorem. It feels like the Cantor function's length should be somewhere between square root of 2 and 2. But in actuality, the Cantor function's length is exactly 2.
Wow. Thank you, Trevor. We'll keep you up to date with more news as it rolls in.
Thank you.
Oh, dude. Interestingly, shallow earthquakes follow the devil's staircase. Small changes are happening all the time in the Earth's crust, but have little to no effect. This is the flat part of the function. A large event, however, triggers big events across a fault area, referred to as a burst. Most earthquake models focus on tension at a single point, but in these Cantor pattern areas, the activity relates to strain on a larger area. The double staircase pattern can be found in large earthquakes in Japan, North China, the United States Great Basin, Australia, and the North Anatolian Fault. This image shows the models of Japan, North China, and the North Anatolian Fault compared to the rest of the world and measures cumulative earthquakes and dates. Hi, and welcome back to my least favorite murder podcast with your host, me, your least favorite murder podcast host. Last week we were in Russia, and before we move on this week, we're going to stay in Russia because we got somebody to talk about. Between 1978 and 1990, Russia was host to the most prolific serial killer of all time. Andrei Chikatilo killed 53 people in a span of 12 years. Surprisingly, the pattern of murders follows the devil's staircase. This is the Chikatilo model, showing cumulative number of kills and time when the people were taken. The shortest time between kills is 3 days, and the longest time between kills is 986 days. Some researchers have noticed a link between psychosis and epilepsy, specifically noticing the distribution of intervals between seizures and murders. They speculate, like how large earthquakes happen in bursts, the firing of neurons. Bursts leads to the psychosis events that contain the planning and execution of the murders or the inducing of seizures in people with epilepsy. The researchers explained that the probability of any neuron firing is actually quite small, but since the intersection of one neuron can connect to thousands others, if that one fires, the others could fire too if they're close to the firing threshold. The model predicts that the killer commits murders when the firing neurons reach the murder zone. It should be noted that Chikatilo's model is very close to the devil's staircase, but not exact. An exact match would imply periods of 1 day between kills, and we know the shortest period is 3 days between Chikatilo's kills. This model does not account for attempted murders though, and that could account for the discrepancies. As researchers move forward, this data is going to be very helpful in trying to catch serial killers down the line. And stay tuned next week as we discuss Hottie Bo Body, Ted Bundy.